now we're just going to talk about encoder properties, kind of. The first hour was mainly on encoding, and this is more on properties of encoders. The 2 lectures tomorrow will be on decoding of convolutional codes. So there's several, we've talked about this a little bit, classifications of encoders as being feed forward and feed back. And there, again, those of you that have worked in linear system theory or dynamic systems, things like this, you kind of know this. It can get quite detailed. We won't want to go into that amount of detail because the practical encoders are usually pretty simple that are used in practice. The notion of equivalent encoders, the notion of catastrophic encoders, some canonical forms for encoders, including minimal encoders, and then something we call a weight enumerating function, which is a way of determining performance of convolutional codes. In block codes, you saw how the minimum distance was important in terms of the error correcting capability, and it's the same thing with convolutional codes, so we'll talk about that a little bit. So feed-forward encoder, this is what we've been discussing for the most part. It corresponds to the generator matrix having polynomials as opposed to rational functions. We did show this, well, it's gone now. We showed this one where we had rational function generator polynomials. Doesn't contain any feedback from encoder output back to the input. So it can be represented as a linear, the outputs can be represented as linear combinations of the current input bit and the past input bits, whatever depending on what the memory order is. The outputs depend on those. There's another terminology, otherwise it doesn't depend on past outputs, it just depends on past inputs. Another term that's used is a non-recursive encoder. And we'll see by contrast a feedback encoder is a so-called recursive encoder. So here's actually a rate 1. This would be a rate 1 encoder. Now any rate 1 encoder doesn't have any error correcting capability. There actually is a use for a rate 1 encoder though in some kinds of concatenated systems, a so-called accumulator encoder, which we'll talk about shortly. But this is just one input, one output, and here's a little state diagram. So if we're in state 0 and we put in a 0, we get an output 0 and we stay in state 0. If we put in a 1, we get an output 1 and we go to state 1 because the next state is a 1 now. And if we're in state 1 and we put in a 0, the new state is a 0 and we get an output of 1. If we are in state 1 and we have an input of 1, those two 1s cancel and we get an output of 0, but we stay in state 1. So this is a simple little two-state encoder diagram for this thing. The generator matrix of this thing, there's only one generator polynomial because there's only one output sequence. And it's 1 plus d. It's taking the current input bit and adding it to the previous input bit. So that's represented by the generator polynomial 1 plus d. And here's another feed-forward encoder. This has memory 3. This is a so-called systematic. I think we get to it on the next slide. But this output sequence is just the input sequence. And this one would be the current input bit plus 1 time unit delayed plus 3 time units delayed. So the generator polynomial here would be 1 plus d cubed. Now, a feedback encoder corresponds to rational generator matrices. And again, we had that little example in the previous lecture, where at least one of the generators is a non-polynomial or a ratio of two polynomials, a rational transfer function. And in terms of the encoder, that means there's a feedback path in the encoder. So in this case, the outputs of feedback encoders they're not just linear combinations of the current input and past inputs, but past outputs are involved also. Okay, and that's why it's referred to as a recursive encoder, because the same bits keep getting encoded over and over again because of the feedback. And therefore, in general, the output is going to depend on an infinite number of past inputs. With the feed-forward type, the outputs are only going to depend on m past inputs. That's it. But with feedback, even though the memory order is m, because it's recursive, you can get this dependency continues throughout the encoding process. So this is a little feedback encoder. It's rate 1/2. It's 2 states, just 1 register stage. And this is a generator matrix. Again, this is of the systematic type where the first output sequence is a 1. Actually, this is fine. And the second output sequence is 1 over 1 plus d. Okay, and otherwise the numerator here of this polynomial depends on where this connection is made. If it's before the delay element, it's a 1. If it was after the delay element, it would be d. And the feedback polynomial is 1 plus d. The 1 representing here, and the d representing what gets fed back from here. So this is the generator matrix. It's a feedback. This is a rational function. So the corresponding encoder corresponding to this generator matrix is a feedback encoder, and this is the state diagram. I guess I won't go through this because it's the same type of thing we've gone through. Here's another feedback encoder. This is rate 1/3 because there's a single input. This is, I'm trying to remember if this is the one we had from the last lecture, or it might be slightly different. I don't remember. 1 input sequence, 3 output sequences. No, it's different because the previous one was a rate 1/2. This is rate 1/3. It's systematic because the first output sequence here is just the input sequence. And then this output sequence is obtained by taking the output of the second delay stage and adding the input to the shift register. So this would be represented, the numerator polynomial for this would be 1 plus d squared. Okay, there's no connection from the 1 time unit delayed. There's no connection from here up to here. So we miss the d term. And the denominator polynomial is, again, using the same approach, 1 plus d squared. And then this output sequence is, again, a rational generator sequence is a rational function. And we have 1 plus d in the numerator and 1 plus d squared in the denominator. So actually, if we wrote this generator, it's a rate 1/3, so the generator matrix has 3 entries, 1 for the systematic part, 1 plus d squared over 1 plus d squared for this output, okay, and then 1 plus d over 1 plus d squared for the last output. So that would be the generator polynomial, or generator matrix, corresponding to this encoder. So again, you always have this, you can look at the encoder diagram, corresponding generator matrix. You can go back and forth between the two. Systematic, we've said this, that k information sequences are unchanged among the n code sequences. They're usually the first k code sequences, or the systematic ones. They don't have to be. Just like we said with block codes, the identity matrix doesn't have to be at the right-hand side of the generator matrix. It could be spread out wherever you want, but that's usually where we put it. It's just a reordering of bits doesn't really, in a code word, doesn't affect anything in terms of the code properties. So it doesn't matter how the ordering is done normally. So this is called a systematic encoder. Its generator matrix is called a systematic generator matrix. So we kind of developed this terminology here of distinguishing between the encoder and the matrix. Okay, a given matrix always can be represented as an encoder, but there can be different realizations, encoder realizations of a generator matrix, which we'll talk about in a second. So here is a rate 1/2 feedback encoder. This is the same one that we just showed. It's systematic, the same example that we just showed, and we have this little state diagram here. I think it's the same one we just showed. Now, what about non-systematic? Just like with block codes, systematic encoders are convenient. Usually, it's a nice property to have, but it's not necessary. And actually, with convolutional codes, depending on how you decode them, but with Viterbi decoding, there's an advantage that accrues to using a non-systematic encoder. So non-systematic encoder, with block codes, there's really no advantage in using non-systematic over systematic. With convolutional codes, depending on how they're decoded, there is. So a non-systematic convolutional encoder, the K information sequences, okay, they're not unchanged at the output. So here is an example. This, I guess, should have said rate 1, right? Because there's one input and one output. And this is the same example we had earlier. We got the generator polynomial is just 1 plus d. There's a single generator polynomial. And this is the state diagram or trellis diagram for this encoder. Now, you can have different generator matrices which will generate the same code. These are called equivalent generator matrices then if they generate the same code. What does that mean? The set of output sequences is the same. Okay. And the encoders then, we refer to the encoders, the two encoders corresponding to the two equivalent generator matrices they'd be referred to as equivalent encoders. Two generator matrices are equivalent if and only if there's a rational invertible matrix. So this can include rational functions, but it has to be invertible such that you can get from G to G primed. So for example, this feedback generator matrix 1 and 1 over 1 plus d is actually equivalent to this feed-forward generator matrix. So we could multiply, we get from here to here by multiplying this by 1 plus d. Okay, and then we get this. So these are equivalent. These generate the same set of sequences. And you may think, well, that sounds a little funny because didn't he just say that with feedback encoders you can get, you get kind of the infinite dependence on the inputs, and with feed-forward encoders you don't have that. You've only got memory 1 in this case. But you can see how this will work. If you're using this encoder and you multiply it by u of d to get an output sequence, okay? And then you say, all right, I'm gonna do this. I want to produce the same output sequence with this encoder. Well, I would simply multiply this encoder by u of d divided by 1 minus d. Okay, because the 1 minus d cancels this and makes it a 1, and it makes this 1 over 1 minus d. So then we have exactly the same thing. So what we have here is the two encoders give the same set of output sequences, but two identical output sequences are produced by different input sequences. So say that we take u of d equal to 1. Okay. U of d equal to 1 here. The first output sequence is going to be 1. The second output sequence is going to be 1 over 1 plus d, which just produces an infinite sequence of 1s. Okay? And that's produced with an input sequence now, a single one, a weight 1 input sequence, produces an output sequence, which the second encoded sequence is an infinite sequence of ones. How do we get that over here? Well, we would have to multiply this matrix by 1 over 1 plus d, which means we'd have to put the all 1 input sequence in here. And then we'd get 1 out here, an infinite sequence of 1s here. So in this case, that output, the same output sequence, a 1 coming out of the first output and an infinite sequence of 1s coming out of the second output. In this case, that sequence is produced with an input 1, weight 1 input sequence. Here it's produced by the all 1 input sequence, an infinite sequence of 1s. So when you have equivalent encoders, the code is the same. The set of code words is the same. But different information sequences produce those code words.
What is TD here?
What is what?
T of D.
T of D is just any invertible, well, it would have to be the right, it would have to match the dimensions here. In this example, it's just a single rational function, because this is a 1 by 2 and this is a 1 by 2. So you've got to have, the only way you get a 1 by 2 from a 1 by 2 is with a 1 by 1. So, but any rational function here which is invertible, it wouldn't have to be 1 plus d. It could be 1 plus d squared. Okay, if I multiplied this by 1 plus d squared, this would be 1 plus d squared. And 1 plus d squared divided by 1 plus d is 1 plus d, because the 1 plus d squared is 1 plus d squared. Okay, okay. In modulo 2 arithmetic, the polynomial 1 plus d squared is equal to 1 plus d squared, because when you multiply 1 plus d by itself, you get the middle term twice and it cancels out. So you could multiply this by 1 plus d squared, and then you'd get something here. This would be 1 plus d squared, and this would be 1 plus d. And then you could get the same, again, you generate the same output sequences, but the input sequence, the correspondence between output and input sequence would again be different. So when you look at these equivalent generator matrices, you don't change the code, but you can change the correspondence between input sequence and output sequence. Now, who cares about that? Why is it important at all? Well, it is important in a turbo coding application, because in turbo codes they use two encoders, and the first encoding is done with a particular input sequence, and then the input sequence is reordered, it's interleaved, and it's permuted, and it affects the second encoder, or it goes into the second encoder. So you have a different correspondence between input sequences and output sequences in those cases, and that can be used to affect a property of a turbo code where it has a desirable weight properties or distance properties. It gives it extremely good performance in the low signal to noise ratio range. I mean, that's getting a little bit beyond what I want to talk about here, but all really I need to say is there are cases where the correspondence between input sequence and output sequences is important. So it's good to be aware of this, and that when we say equivalent encoders, we have to be careful. It doesn't mean equivalent in all aspects. It just means this set of code words is the same. Now now you can always in terms of systematic encoders, you can always take a non-systematic encoder and convert it to a systematic encoder. Okay. I mean, one of the things you want to be careful of is generally speaking, you'd like to use an encoder, and I think you can see a little bit with this example of equivalent encoders. Once these encoders get a little bit more complicated than the kind of simple examples we consider here, there could be a lot of equivalent encoders which would generate the same code. And one of the things you want to do because of the complexity issue is always try to use an encoder which has as few shift register stages as possible, so you have the minimum number of states. And also, if systematic is important to you, you might want to use a systematic encoder. So you could convert any non-systematic encoder to a systematic encoder, similar to the way you'd convert a non-systematic generator matrix of a block code to a systematic generator matrix by doing row operations on the generator matrix to produce a matrix which has an identity in k columns. And you can do the same thing here in the polynomial domain. Now, the thing you want to be careful of is, in doing this, you would not want to produce an encoder which had more states, okay, than the one that you started with. But the way you do it, and I'm not going to go through all the details, I don't think, because this lecture's got a lot in it, and it's late in the day. But basically, your objective is to get the first two columns here to be an identity matrix. So in order for that to happen, you got to get a 1 here. Well, how do you get a 1 here? You divide 1 plus d by 1 plus d. Okay? And row operations are always, you can add rows or you can multiply a row by anything without changing the subspace, which defines the code. The same as whether, again, with convolutional codes, we have generator matrices here which are made up of polynomials or rational functions. With block codes, they're just binary generator matrices, but the idea is the same. So if we multiply this first row by 1 over 1 plus d, we get this. Okay? And then, okay, what's the next thing we want to do? We want to get a 0 here. So how can we do that? We can multiply the first row by d and add it to the second row, and that'll knock out this d. So that's what we do. We multiply the first row by d, add it to the second d. That gives us this. Now, by multiplying this by 1 over 1 plus d, we already got feedback here. And when we multiply this by d and add it down in here, this feedback stays in. So we've got it down here now. Now the next thing we want to do is get a 1 down here. Okay? So we want to multiply this row by the inverse of this so we can get a 1. And we do that here. That gives us this polynomial over here. And then the last step is we're going to want to multiply this row by this, by this, and then add it up here to get a 0 here. So we do that. We multiply row 2 by d over 1 plus d, add it to row 1, and we get this. So we wind up with an equivalent generator matrix because we've just done linear operations on the rows, but now it's in systematic form. And it's got 2 rational parity check functions here. This is the systematic part. This is the parity part. This is was a rate 2/3 encoder. Maybe I didn't say that. This is a rate 2/3 encoder. It's got 2 rows and 3 columns. So there's 1 parity sequence, and these are the 2 parity generators in polynomial form or in rational function form. And there's nothing higher than the power of d here, so we still got memory 2. We could still realize this with shift register of length 2. So we haven't increased the number of states. So you can always do that. If you've got non-systematic, you can convert it to systematic. Okay, now you may, in general, you may require more states, which you wouldn't want to do. But if you can do it with the same number of states, usually it's advantageous to do that. There's a notion of an encoder being catastrophic. If you can encode an information symbol with infinitely many non-zero symbols into a code sequence with finitely many non-zero symbols. So if you put, the idea is if you put an infinite weight sequence in, can you get a finite weight sequence out? Okay, you may say, who cares? Why would I care about that? Well, what the decoder is trying to do is take the received sequence and recover the information sequence and make as few errors as possible. Now, if your code word has a finite number of ones, say it's a small number of ones, then it would take only a few errors on the channel. Again, we're thinking of a binary symmetric channel here. It's the easiest thing to think about. A few errors on the channel that would change that code word into the all zero sequence. If you had only a finite number of ones, if you had errors in just those positions, then your received sequence would be all zero. Since this is a linear code, any decoder is going to decode the all zero received sequence into the all zero information sequence. But if your actual information sequence had an infinite number of ones in it, you'd make an infinite number of errors. So you don't want to have an encoder for which you could produce an infinite number of errors with decoding errors with a finite number of channel errors. Or you don't want to have to put it a little more practically, you don't want to have a small number of errors on a channel result in a large number of bit errors in decoding the information sequence. So this is what you're trying to avoid. So this encoder, if we have the input sequence 1 over 1 plus d, which is the all 1 sequence, then the output sequence, it's a factor of this. We just get 1. And as I said, 1 plus d squared divided by 1 plus d is just 1 plus d. Output sequence would have only weight 3. So we'd have a very long sequence of weight 3. If we had 3 errors in the wrong spot, we'd make a huge number of decoding errors because we'd think that the input sequence was 0, whereas actually it was all ones. So you want to avoid encoding matrices like this. Now, you could say, so actually what causes a problem like this is if you have a common factor, at least for rate 1 over n encoders. If you have a common factor in g of d, then you divide by that common factor and you'd get a finite weight sequences, but the input sequence divided by that common factor would have infinite weight. So you want to avoid common factors in the generator polynomial. I mean, this is just, when you have a code, you want to encode it with the best encoder. And you don't want to use a catastrophic encoder. Generally, they would have more states than an equivalent encoder anyway, so you wouldn't use it for that reason anyway. Now, there are, and again, this gets into the relationship with linear system theory. I'm not going to spend much time on this. It's just something that we'll mention. There are some canonical forms for realizing generator matrices with rational function entries in terms of linear system theory. One is called a controller canonical form, and it uses k shift registers, 1 for each input sequence, and there are n adders, 1 for each output sequence, are external to the shift register. Otherwise, we don't have, like when we showed feedback encoders, sometimes we had an adder. No, we didn't have that yet. No, we haven't had an example of that. But you can have realizations where you will have adders internal to the shift register. But this form doesn't allow that. And this is just a general picture here of realizing a rational function in this form. So the numerator polynomial, the f's here, are represented like this. There's adders here, and they are connected to the stages of the shift register with whatever these coefficients are. And again, these would generally be binary. And then the denominator polynomial, the q's, is represented by these feedbacks, taps off the shift register, added up and fed back to the input here. So this is a general form of realizing, so for each input sequence would have a shift register like this with some feedback polynomial and some adders out here to produce an output sequence, one or more output sequences. Pardon? Well, for this little picture it is, right. Right, but this could be part of a bigger encoder. It would be, yeah, you could look at it that way. Now there's another kind of general form from system theory that is a so-called observer canonical form. Uses actually n shift registers, one for each output. K input sequences actually enter adders which are internal to the shift registers. We'll see what this looks like in a second. And again, just a general rate 1 kind of canonical form encoder realization would look like this. So you have adders here internal to the shift register, and you have the numerator polynomial determining the connections into these adders, and the denominator polynomial here determining the fed back connections from the output to the input and to the internal adders. So very generally, if you have a low rate encoder, like 1 over n, where n is more than 2, rate 1/2 is usually easy, okay, to see how to best to do the encoding. But if you have lower rate encoders, generally speaking, this is the kind of encoder realization you want to use, because you've got only one input, you need only one shift register. Okay? And it's very straightforward to form these. These are kind of the examples we've been looking at. If you have high rate encoders like k-1 or n-1 over n encoders, 2/3, 3/4, things like this, this controller observer canonical form is often the most efficient, particularly if the coders are systematic. Because if they're systematic, you need one of these shift registers for each output, but if the encoder is systematic, then n-1 of the outputs are systematic. And the encoding is just, transfer function is just a 1 in those cases. So there's no shift register, it's just a connection. So you need only one shift register then for the parity sequence. And that's easy to generate in this form. If you try to do it with the other form, it's more complicated. So here's an example, rate 2/3 systematic, feed forward encoder. This is feed forward. Oftentimes they're feedback. The type of encoders that were used in modem design, generally a lot of rate 2/3 or 3/4 encoders with feedback polynomials over here for the parity. We didn't really develop this at all, but the same thing, there's a relationship with the parity check matrix here, just like there is with block codes. Otherwise, there's an H of D matrix such that GH of D is equal to 0. And in this case, and when G is systematic, just like with block codes, it's easy to write down the systematic parity check matrix. You just take the two parity generators here out of the generator matrix, and those become the first two entries in the parity check matrix, and then this is the systematic part of the parity check matrix. There's only one parity check sequence in a rate 2/3 encoder, so this is just a 1/3. But if you have this in systematic form, you have this immediately. So actually this encoder, in this particular example, we'll show it here in a minute, if we do the controller canonical form, which I said was better for the low rate encoders, that's, you wind up having to use memory total constraint length 3. Because you're going to have 2 input sequences, 1 shift register for each. This shift register is going to have memory order 2. This one's going to have memory order 1. So the total memory will be 3. The overall constraint length will be 3. If you do this with an observer canonical form, which I said is usually the better way to do high rate encoders, particularly if they're systematic, it's basically given by, you get the connections off of the parity check matrix, and you need only 2 delay elements. So you have fewer states, 4 instead of 8. So here's the controller canonical form. You can see it. You need the parity sequence. You need 1 plus d squared off of the first shift register and 1 plus d off the second one. So here's the first shift register, 1 plus d squared. Here's the second shift register, 1 plus d, and you need all those inputs here to give you the parity sequence. The other 2 outputs are the systematic outputs. But you need 3 register stages if you want to use controller canonical form, 8 states. Okay. If you use observer canonical form, you get it this way, with 4 states. And the connections, and you can read this right off the parity check matrix, the connections, the first set of connections are 1 plus d squared. This determines the first output sequence. 1 plus d determines the second output sequence. So, well, no, I said that backwards. This is the third output sequence, the second, and the systematic is the first. So here's the systematic. Here's the 2 systematic sequences, and then the parity sequence you get by 1 plus d squared from the first input sequence, and 1 plus d from the second input sequence. Whoops. So there's no connection here. So here's the 1 plus d from the U2 input, and here's the 1 plus d squared from the input sequence 1. So this is the 1 plus d squared from input sequence 1 and the 1 plus d from input sequence 2. Or you can look at it as from the generator matrix point of view too. The 1 plus d squared associated with input sequence 1, the 1 plus d associated with input sequence 2. These are, again, they're equivalent ways of looking at it. So the point here is that you can get easier. Some of these encoder realizations, I mean, this is the same. I mean, here's the generator matrix, and it generates a particular code. But there are different ways of realizing the generator matrix. One realization gives you 8 states, the other realization gives you 4 states. The concept of a minimal encoder, you could have a generator matrix which is minimal if its number of states is minimal over all equivalent generator matrices. But a particular generator matrix can have different realizations, like these 2 we just showed. And a minimal encoder, you have to start with a minimal encoding matrix and then use the encoder realization which has the minimum number of memory elements. This gets into the weeds a little bit, but it would be more important probably if we often used big encoders with lots of states where these issues you could have significant difference between some realizations and others. For simple encoders, there's not too much difference. But this little example we showed just here was not so complicated. A rate 2/3 systematic encoder where one realization gave us 8 states, the other one gave us 4 states. The idea is we always want to use a minimal encoder because that reduces the complexity of decoding. So this is maybe a little bit more than we need for this class on this stuff because it's, like I said, we're not doing coded modulation, trellis coded modulation for modems where these kind of high rate encoders are important and some of these considerations come into play. And we're also not going to be able to spend any time in class on turbo codes where this idea of the mapping between, the correspondence between input sequences and output sequences becomes important. Question?
The generator is written in systematic form. In case of convolutional code, then we can similarly change it into parity check code, right? Parity check matrix.
Yeah.
We can convert.
Right. We didn't explain that here, but it just, we have that one example, but you can kind of see how it goes. And it's analogous to what you do with the block codes. Once you get it in systematic form, you can convert. With the block codes, you take the transpose of the parity check matrix, and that's actually what you do here, too. I mean, this is the parity check part of the generator matrix, and you take the transpose of that and put it here. So that's it. Yeah. So now, distance properties. With convolutional codes, we talk about free distance. It's a different term rather than minimum distance. Why? Because there's not a fixed code word length. With block codes, all the code words of length n, you talk about the minimum distance between any 2 code words of length n, or the minimum weight of any code word of length n. With convolutional codes, code words can be of different lengths. I mean, if you think in terms of the trellis diagram, you can have short code words which leave the all zero state, wander around in the trellis for a while, and then come back to the all zero state and stay at the all zero state. Or you can think in terms of the state diagram. And those are not going to have high weight because they're short. They can, once they're in the all zero state, they're just going to generate zeros. You can have other sequences which wander through the trellis forever, okay, before coming back to the all zero state. And those are going to have higher weights. So you have short code words with low weight, long code words with higher weight. And it's actually the combination of all possible weights that the encoder can generate that is going to determine how well it performs with maximum likelihood decoding, which we'll discuss tomorrow morning. The Viterbi decoding algorithm is the maximum likelihood decoding algorithm for convolutional codes. So the free distance is just the minimum distance between any 2 code sequences that are generated by different information sequences. Obviously, if the information sequence are the same, the code sequence are going to be the same. And that distance is going to be 0. So this is, these are code words V and V prime corresponding to the information sequences U and U primed. So it's the minimum Hamming distance between any 2 code sequences in the code, but notice that there's not a notion that these are necessarily of the same length. I mean, you could consider them of the same length if you want to say, all right, we're eventually going to terminate the code, consider all code words of that length. But some of these code words will have a whole bunch of zeros at the end because they've remerged with the all zero state, and their non-zero part will only be maybe at the beginning or in part of the code word. So it's also, because it's linear, it's the minimum Hamming weight of any non-zero sequence. So you think of the state diagram or the trellis diagram, you leave the all zero state and eventually you come back. What's the lowest weight way you can leave the all zero state and get back? That's the minimum free distance of the code. Now the entire weight distribution, not just the free distance, is important in determining the performance of the code. It can be contained, now I'm going to go through this, there's a lot of words here. And it's, you know, at, what is it, 10 to 5 in the afternoon? it's taxing your brain to try to think through all these words. So we will do an example. I'll go through the words quickly. We'll do an example. Hopefully it'll be a little clearer with the example. So we obtain, you can get the complete weight distribution of a convolutional encoder by a method that we're going to describe here based on the state diagram. Now, the only problem is it's only practical to do for encoders with small memory. But still, it gives us a lot of insight as to how convolutional codes perform with maximum likelihood decoding. So you take the all zero state, you split it into two states, an initial and a final state. And that little self loop around the all zero state, you just throw that away. Because that has nothing to do with weight. It just gives you zeros. You can cycle around that forever and you don't get any weight. So we're only interested in weight here. Now you take then each branch of the state diagram then of this modified state diagram is labeled with a so-called branch gain. This comes from systems analysis again. This technique has to do with flow graphs, analyzing the gain of a flow graph. Even in circuits, this was originally done, I think. So this branch gain, you just label x to the I, where I is the weight of the n output bits on that branch. So in a rate 1/2 code, we would label each branch either x to the 0, x to the 1, or x to the 2, depending on the weight on that branch. Now, then every path connecting the initial state to the final state is a non-zero code word. Otherwise, you leave the zero state, you wander through the state diagram, and come back to the zero state. You generate some weight in doing that. The path gain of that path through the trellis, or state diagram, is just the product of the branch gains. By taking the product of the branch gains, you're adding the exponents. You're adding the weight on each branch. And the weight of a code sequence when you're finished doing this is the power of x and the path gain. Okay, when you multiply all these branch gains together, you get the path gain, and the power of x is going to be the weight of that path. Now there's a formula in system theory called Mason's gain formula, which can be used to compute the transfer function. In general, it's called a transfer function in system theory. In coding, we tend to call it more the generating function or the weight enumerator function. And it's simply a sum of x to the i's, which are the code words of weight I, and ai would be the number of code words of weight I. So it tells you all the weights of all the code words in the code. And you can get this function by applying this formula to this modified state diagram. Now there's a few things that you need to know to calculate this thing. A forward path is any path that connects the initial state to the final state. It doesn't repeat any states. A loop is something in the state diagram that cycles around and comes back to the same state. And it doesn't go through any others, doesn't repeat any other state. And then you have the concept of non-touching loops. In the state diagram, you can have loops. They may touch each other, have a state in common, or they may be totally disjoint. If they're disjoint, they're non-touching. Now, any forward path is going to have a gain associated with it, the product of the x sub i's along that forward path. And any loop is going to have a gain associated with it, just the product of the x sub i's around the loop. And we're going to have a certain set of loops, and this is the notation we use to designate the set of loops in our modified state diagram. And then we're going to have pairs of non-touching loops, two loops which don't touch. And then we're going to have maybe triples of non-touching loops, a set of 3 loops which have no states in common. Okay, then we define a parameter delta, which is just 1 minus the sum of these loop gains plus the product of the loop gains of pairs of non-touching loops minus the product of the loop gains of triples of non-touching loops, et cetera, et cetera, et cetera. Now, thankfully, the type of codes for which you can really do this, I think I've done a couple of examples. If I really wanted to mess up a class and give them all lousy grades, okay, I would give them an example where they had the triples of non-touching loops, and they could never get those right, you know. Not in a 1 hour exam period or something like that. I mean, we don't run into the types of codes that you can do this for practically, you're not going to run into anything beyond this, certainly. Now there's one other concept is a subgraph that you get when you take all the states that the ith forward path goes through and all the branches connecting, and whatever is left, you call it the subgraph associated with the ith forward path. And then that subgraph will have a little delta associated with that, defined the same way as this. Now, this is always going to be simpler to get than this because it's a smaller graph. Okay, then given all that terminology and notation, you get the transfer function by taking the ith forward path and multiplying the gain of the ith forward path, multiplying it by the delta associated with the ith forward path, and summing over all forward paths in the graph, and then dividing by the overall delta of the graph. And you get, we'll see an example here, you get a function which tells you exactly how many code words there are of every weight. Now, you can augment this, and there's a reason for doing this. If you add a y to every branch which corresponds to a non-zero information bit, otherwise a 1 information bit, then when you compute the generating function for that, including the y, you're going to get the information weight associated with each path. So you'll get the correspondence between information weight and code weight, which again, as I said, is important. It turns out to be important in analyzing turbo codes, the performance of turbo codes. And if you label every branch with a z, then the z will keep track of the length of the code words, just how long they are. How long the code, from the time it left the all zero state and returned to the all zero state, how many branches did it go through? And so if you include these other labels on the branches, you get a generator function like this, which is this coefficient here is the number of code sequences of weight I which have information sequence weight j associated with them and are L branches long. Okay, you can get pretty complicated. Okay. If any of you have ever seen my book, you'll see some of these things worked out in the chapter on turbo codes. I'm going to skip this. This is input-output weight enumerating function and conditional weight enumerating function. This is just obtained from what we just saw by forgetting about the length property. And it just relates the input weights and the output weights. Again, it's useful for analyzing turbo codes because the two encoders have different correspondence between input weights. Even though they're the same encoder, they have a different correspondence between input weights and output weights because of the interleaver. But I'm not going to, let's just try to go through this for our favorite little example here. So here's our state diagram. Okay. And here's our modified state diagram. Notice we've taken the zero state and split it into two. Whoops. A beginning zero state and an ending zero state. And also the little self loop around the zero state with weight 0 isn't there anymore. Okay, and then we've taken the rest of the diagram, we've redrawn it a little bit, but this state can go here. That's this state. Now, in this case, I've used kind of a generic label for the states S1, S3, and S2, I guess. The binary representation of those states. You don't have to do that. And each branch here is labeled with a power of x corresponding to the number of non-zero output bits on that branch. So here, in taking this branch, we have weight 2, so we'd get an x squared. And then from going here, we go either to this state or to this state. Either way, we have weight 1. So here's our weight 2, and then whether we go this way or this way, we have weight 1. We have x to the first power. Here we have x squared. Same way up here. You can go either stay here or go down here. Either way with weight 1, so you get x. Here is the one where you go back from this state to this state with 0 weight. So this is x to the 0, or 1. And then when you return to the all 0 state, you pick up weight 2. So this is the modified state diagram corresponding to the state diagram that we started with. There's 3 loops in here. So first of all, we got to deal with this delta thing. Well, here's a loop. Okay, and here's a loop. And those two don't touch, by the way. And the third loop is this one. And that one does touch both of the other two. So we have 3 loops. We have 1 pair of non-touching loops. So this shouldn't be too painful. The self loop around S3 has gain 1. Okay, so x to the first power. The S1, S2, S1 loop, that's this one, has gain, total gain, x to the first power times x to the 0 power is x to the first power. So that's that gain. And then the final loop, the big one, has gain x times x times x to the 0, so it's x squared. So this loop has gain x squared. So pairs of non-touching loops, well, there was just this one and this one. And the product of their 2 gains is x squared. And there are no triples of non-touching loops. So our delta then is 1 minus the sum of the loop gains, these 3 guys, plus the product of the loop gains of the non-touching loops. So these 3 are, there's an x, there's an x, there's an x squared, so we get a minus 2x and a minus x squared. We're not doing modulo 2 arithmetic here. This is real arithmetic, right? Yeah. Because we're counting. We're just counting. So, and then this product of the loop gains is x squared, and these cancel, and you just get 1 minus 2x. So it's not bad. There are 2 forward paths in this thing. Remember, forward path, it can't go through any state twice. So you got this guy. Okay, and since you found that one, I'll call this one this gal or woman. Okay. This is a forward path, and this is a forward path. Now, this forward path touches every state, so there's no subgraph associated with it. This forward path doesn't touch this state. So this is the little subgraph associated with this forward path. And its delta is just 1 over 1 minus x. It's got 1 loop. Its gain is x, 1 over 1 minus x. The first forward, or let's get the gains here. The first forward path has gain 5, x squared times x squared. And this one has gain 6, x squared times x times x times x squared. So there's one with gain 5 and one with gain 6. So there's the one with gain 5. There's the one with gain 6. The subgraph, as I said, has a delta of 1 minus x. And the other one, the other subgraph is empty. There are no states in it, so its delta would be 1. There's no loops to subtract from it. And the transfer function then is the f1 times the delta 1 plus the f2 times the delta 2 divided by the delta. And this is x to the 5th minus x to the 6th plus x to the 6th, so it's just x to the 5th. And this is 1 minus 2x. And if you divide this out, just polynomial division, you get x to the 5th plus 2x to the 6th plus 4x to the 7th. And each higher weight is double the number of code words of that weight. So what this says is that the free distance of this code is 5. That's the minimum weight. And that was just that straight. You basically just leave the all zero state and you get back there as fast as you can, and you pick up weight 5. And but there's 2 code words of weight 6, 4 of weight 7, 8 of weight 8. So it gives you a complete weight distribution for the code. Depending on, you'd keep going here, depending on how long the input sequence was. If you had an input sequence of length 100, you'd truncate this thing because you wouldn't go beyond length 100. But you could get the complete weight distribution. And this allows you, we won't do this in this class again because we're short of time to cover some of this background material, but you can use this analysis to get a bound. If any of you are familiar with the union bound, you can use this analysis to get a union bound on the error probability of a maximum likelihood decoder for a convolutional code of the type we're going to discuss tomorrow, the Viterbi algorithm. So this is very nice for analysis. The only problem is if you get beyond memory about 4, it's really impossible to compute this thing anymore. So for short codes, you can get this. Now, having said that, a lot of the codes that are used in practice are short codes. Okay, in the wireless standards, now some of them are getting pretty long. They're getting up to memory 8 or 9 or something like that. But some of the earlier ones used memories 3 or 4, and some of the trellis-coded modulation schemes use small memories also, high-rate codes with small memories. So you could, in fact, analyze the weight distribution of those codes and come up with a nice bound on their performance based on Viterbi decoding using this method. Now, if you augment the state diagram, you get a z on every branch, and you get a y on the branches that correspond to an input of 1. And then if you apply exactly the same technique, except you got 3 variables now instead of 1, you get this thing, which tells you that your weight 5 code word is generated by an input sequence of weight 1, and its length is 3 branches or 3 time units. And then the 2 weight 6 sequences are both generated by input sequences of weight 2. One is of length 4, one is of length 5, etc. So it gives you more detailed information about the code. And in particular, the X and Y information is useful if you're trying to analyze a turbo code. That's this input-output weight enumerator that we showed briefly. So I think that's it. We're a few minutes over time, but not too bad. Are there questions? Well, the original turbo code had memory 4. It was a rate 1/2 systematic feedback encoder with memory 4. And in the standards, yeah, they use so that would be 16 states. They've used 8 states, I think, is used in the state. You don't need a lot of states because the power of the turbo code comes from the concatenation of 2 encoders separated by an interleaver, a random interleaver, or a random-like interleaver. And so that combines 2 low-complexity encoders in a way in which you get the effect is that you get a very powerful code. But yeah, they're not big encoders. Yeah, you can analyze. Like I said in my book, I've got a couple of examples worked out in quite a lot of detail. I mean, it's a little tricky because the code word is made up of two encoded sequences, one coming from one encoder and another coming from a second encoder, which has the information sequence input, same weight, but reordered in a different way. So you have to combine this kind of analysis for the two encoders. It's something called a uniform interleaver analysis. It's an averaging. But basically it's this technique modified to be able to handle turbo codes, and you can analyze get their weight distribution and analyze their performance that way. Now, I will say that the analysis that you wind up with there, that would assume that you're using maximum likelihood decoding on that turbo code. That's not the way they're decoded. They're decoded iteratively with individual map decoders. The BCGR algorithm, which we'll talk about tomorrow morning also. But it's not one overall BCGR decoder. It's not an optimum decoder. It's an optimum decoder on the individual component codes, but on the overall code, it's iterative, and it's suboptimum in general, although it works quite well. So this analysis doesn't apply exactly there because the decoding method is different. But it gives you a good approximation to the performance. Yeah. Any other questions then? Yeah.
In this finding this transfer function, from start to end state, we find the minimum weight.
That's the free distance.
Yeah.
Yeah.
So how does it help us to analyze the performance?
Well,
What does free distance indicate in terms of?
okay, well, it's just that you can compute, if you know the weights of all the code words. Remember, what errors occur when the noise will drive the receive sequence closer to an incorrect code word than to the code word that was actually transmitted. So you have Gaussian noise on the channel, and you can compute the probability that if you know exactly what the non-zero code words are, you can assume that all zero code word is transmitted, and then you compute the probability that you get errors on the channel in those positions, the number of positions corresponding to the code word weights. So that with the minimum free distance 5, there are channel error sequences of weight 3 that could cause an error. This could get you closer to the weight 5 code word than to the weight 0 code word. So, but they have to occur in certain positions, and it depends. The analysis actually, we won't go into this, but it depends on how the decoding is done. You'll see tomorrow how the decoding is done, and then the analysis takes off on that because it's an analysis of the error probability of that particular decoding method. It has to do with comparing paths which merge into a particular state, a correct path and an incorrect path, and then how many errors it would take to cause on a channel to cause the correct path to be mistaken for the incorrect path. But the analysis is very tied. It is tied to the way the Viterbi algorithm works. So it's not exactly the way you do the analysis for block codes, but it's similar to that.
So what is the maximum limit for calculating the transfer function? If the memory exceeds more than what?
I think I did one in memory 4 once. I think if the memory is 5, it gets pretty hard. I mean, it depends. You could make, I suppose you could design the encoder to make it easy to calculate this. Actually, I remember Bob McLeese gave a talk on that once.
Actually, like you could with Maple, the software like
Yeah, yeah.
Maple and
Well, I'm just talking about doing by hand. Yeah,
Oh,
yeah, yeah. How far can you go with Maple?
Like after memory 6 and 7,
Okay.
the matrix manipulation, like inversion, it just messes
Okay, so you can do 6. So you could do the NASA standard code then.
up. Right, so it should be.
Okay.
I think 6 is doable. After
Okay.
that, it becomes tough.
Okay. Okay.
Control a canonical form related to the concept of controllability in system.
Yeah, sure. Yeah.
You can control the state.
Yeah.
One state of your
Yeah.
Compare the names.
Yeah. Yeah.
You can control the state of
Yeah, that's because the inputs feed into the shift register so that you can, yeah. You can't control the states if the inputs don't feed into the shift register, but if they do, then you can control, you can drive the states with the next set of inputs, yeah. It's exactly the same stuff. I mean, that's why I think I was telling you the other day that there's a lot of system theory people contributed a lot to basic theory of convolutional encoders and things like that, particularly in the early days. The only problem was a lot of that theory doesn't help us determine the distance properties of the code, which is what really determines its performance.